Recursion trees. Controlling the fundamentals stands at the cornerstone of controlling any topic. In our case, in order to be a good software developer, it's not enough or even not at all important to control the latest technology, such as the latest Java or the latest JavaScript or the latest big data technology. What's really important is the basics. And the basics in computer science are math, statistics, algorithms, and computer structure. When the Apple company started, Steve Wozniak was one of the co-founders. What gave Apple and Steve the competitive advantage over other companies was Wozniak's deep understanding of programming and of computer structure. He built the computers from scratch, he designed them from scratch, and he wrote all the code that operated them. He could not have done this without deep understanding of algorithms and programming and computer structure and math. This is what gave him the ability to create the first desktop computer, which was much less costly than the competitors' ones. Not that there were many at the time. And by the way, if we are talking about Apple founders, there were 3 founders. The first was Wozniak, the second was Jobs, which handled more of the product, where Wozniak handled more of the technical side. And the third one was the one who was responsible for building the company structure and being responsible for its growth. And each of them was extremely important. It was not only Wozniak and Jobs. But that's a topic for another episode. And with that, let's get going with recursion trees. Problems. Algorithms are the basis of problem solving. This is like the ground-based theory for problem solving. One of the topmost structures and algorithms for solving problems is named in the general name divide and conquer. In divide and conquer, you take one problem, let's say you have n items, and you divide them into sub-problems. Let's say we took the n items that we have and we divided them into 2. So now we have 2 sub-problems, each with half of n item, where we need to solve the problem for each sub-problem. With the hope that because each sub-problem is smaller enough, smaller than a larger problem, then it would be easier and also the cost would be lower than solving the top problem. Then we combine each of the sub-problems, and we in most cases need to invest some additional time in order to combine the solutions of the 2 sub-problems. In case we divided the main problem into 2, and then we have the result of the top problem. When you do such a problem and you use the divide and conquer technique for solving such problems, a question is raised. What is the running time? How much time does it take us to solve such a problem with this technique? This technique of divide and conquer is usually and commonly used in recursions. This is where recursion trees come into place. Recursion trees are a pictorial, an intuitive, and a graphical representation of the divide and conquer technique for problem solving. They are great for getting an intuition into how long would it take for our algorithms to run. And the best thing is that you could actually draw a picture of that tree and get the immediate intuition of how long would this algorithm run. Why do we draw a tree? Except for the fact that this technique is called recursion trees, it's because we are reducing the problem that we had into subcomponents and solving each subcomponent and then merging the results. So just like in a tree where we have a root node, in our case the root node is our basic problem that we are going to divide. The value of the root node and the value of each node, we define it as the time it's going to take for the algorithm to run on that node. So while we could say that the root node is the whole problem, this is not the value that we assign to it. We assign to it only the value that in our divide and conquer algorithm it's going to take for the root node, which is simply the merging of the sub-problems. So it's not the whole time that it would take the algorithm, it's the time that is left after you assume that you solved all the children to run, because we delegate the problem into the subnodes. So every node, like you should imagine that it's holding the time that it's actually computing. And the total running time is the sum of the time of all the nodes, the sum of the value of all the nodes. Then we start with the root node and we draw arrows into multiple children nodes where each child is a subproblem. The value of each child is the time that it's going to take for the algorithm to run on to solve that child exactly. But you need to remember that in order to solve that child, you draw arrows into its subchildren. So the time is only the time that you waste on that specific node. It's not the whole time to calculate the whole algorithm, it's only the time like to combine the result of the sub-children. To be more specific, let's say that we have an algorithm which is recursive, and this is the reason that we use recursion trees, because our algorithm is recursive. And this is how we are able to reduce our problem into sub-problems, because we do the divide and conquer, we do the recursive calls. So if we specify, we define the time for the non-recursive part. The non-recursive part is the part where you do like the merging. If you do merge, then it's the merging, or the time that you do to combine the sum problems, the solution of the sum problems into the main problem. So if we said that the time on the main node where we had n elements, in order to do the non-recursive part is O of f of n, some function of n, then in other words, it's linearly relational to the number of elements that we had in that node. So if we have our recursive calls, and by our recursive calls, we say that from the main node, we had like our children, because we divided the main call into our sub-calls. But in each such sub-call, we need also to specify another parameter. So the first parameter was n, the number of elements that we have totally. The second was the time that we spent on the non-recursive part, which is O of f of n. The third parameter is for how many subproblems we divide. We said that we divide it into our recursive calls. So if we divided it into 4 subproblems, then r is 4. And the fourth element is how many elements we originally had n elements, how many elements we have in each subproblem. In the usual case, we have like n divided by c, where c is the divisor. So now the time that we are going to spend on the non-recursive part on each subproblem is O of f of n divided by c time to solve each such subproblem in a linear time that it takes. Therefore, the total time in the general way for our algorithm would be t of n, the time to solve the problem of n, is equal to, in the general way, to r, which is the number of recursive calls that we have, times the time that it's going to take for each subproblem. And because in each subproblem we have n divided by c elements, then it's going to be r multiplied by time to compute it's a problem, where it's a problem is n divided by c, plus the time to combine on the element, which is f of n. So t of n was the total time that it takes to solve the problem that we don't know how much time it takes, but we know that we have our recursive calls. So we know that we have r on the equation of how much time does it take to do t of n. In addition, we know that we have n divided by c elements in each subproblem, so we have r multiplied by t of n divided by c. The total time, this is the total time that it would take us to solve each of the subproblems. But it's not enough to solve each of the subproblems. We then need to invest some more time in order to reach the main problem. We can't just solve each of the subproblems and stop there. We need to combine it. So the time to combine the subproblems is f of n. So this is the general equation for solving recursion trees. T of n is r multiplied by t of n divided by c plus f of n. When we solve a problem with recursion, we have basis cases, right? So in our case, when we have drawn the tree, then the leaves of the tree are actually representing the base cases. And usually the base cases in recursion takes a constant time to execute. So you can just assume that t of n, the time that it takes to compute the base cases, is constant. It's 1. Each of the base cases. The general structure for a tree with r subproblems for each level, when in each level you decrease the number of items from n into n divided by c in each level, means that the next level, each node would have n divided by c squared, and up to n divided by c to the power of the level of the tree, where the level is the number of levels that you have on the tree. The level of the tree, you can compute it as log base c of n. So this brings us to the ground truth of the overall time complexity for the recursion tree in the most general way, which is t of n is sigma from I starting from 0 up to L of R, the number of subproblems that you have, power to the I, and all this multiplied by the time it's going to take to combine each of the subproblems, which is f of n divided by c to the power of I. When we look at this formula for the general time of the recursion tree, this is the general time that it's going to take to compute the recursion tree to execute the time. Then we need to remember that we have 3 distinct cases, because we assumed now that on each level we have n divided by c elements. Okay, because in merge sort you divide the items by 2, so in each subproblems you have half of the item, but this is not necessarily always the case. So we have 3 cases. The first case is where the tree is very shallow, which means that the number of items decreases exponentially in each level. The second case is like the balanced case, where in each level we decrease a balanced amount of nodes. This is very typical of merge sort. Okay, so it's very balanced. It's a log of a tree. The third case is where you're not able to decrease enough items on each level of the tree. So on the first level you have n items, then on the second level you have n minus 1 item, then on the third level you have n minus 2 items. So it's more like a line than a tree. In the first case, where the items decrease exponentially on each level, then this is the case where in every level of the tree, then you have a constant factor smaller than the previous term. This is the case where you decrease the time complexity so drastically that the actual time to execute the actual elements is simply the combination time that it takes to combine the elements. In the second case, this is the case that we know from standard sorting algorithms such as merge sort in the average cases, where all terms in each level are equal. In this case, we have the standard sorting time complexity of ffn log n. This is like the balance case, where in each level you divide the items by half. So what this all means is that while we could look at the general formula that we provided on the previous case, you don't need really this formula, because what you can do is look at the tree and tell yourself, is this tree decreasing exponentially? Is this tree decreasing by the number of items divided by 2? Or is this tree looking like a line? And immediately when you identify the shape of the tree, you can know how much time it's going to take, because if this tree is decreasing by 1, so you have n elements at the top, and then n minus 1 elements at the next level, then you know that the time complexity for this tree to run is actually of n power 2. But if you see that this tree has the shape of half of the items in each node, in each level, then you know that this is the shape of merge sort. This is the shape of n log n. To sum up, when we have a divide and conquer solution, or when we have a problem that we solve with recursion, then we can draw a recursion tree, look at it, see its shape, and from that we can understand pretty much how much time would it take to, how much time would the running time be of this algorithm. We look at the subproblems, we look at how many subproblems do we have for each problem. We look at how many items do we have in each subproblem. We look at the span of the tree. We look at the number of levels that we see on the tree. And depending on that, we can say immediately how much time and how efficient this algorithm would be. So this is the power of recursion trees. You draw the shape of the tree by how your solution looks, and when you draw the shape of the tree, you look at it, you look at the shape of the tree, and you can know intuitively what is the running time of this algorithm, and this is very powerful. So I think this was very interesting, and we'll see you next time.